model a molecule as a small piece of wood, and we put a negatively charged particle on one end, and we put a positively charged end on the other, kind of like a water molecule, okay? And we're going to subject that to an electric field going in this direction, okay? So the electric field is going to be going in this direction. L is the length between the two ends of the particles. Now we know that torque equals force times radius, right? So since torque equals force times radius, and force equals Ek, what's one simple substitution that we could do?
Torque equals Ek radius.
We could put torque
Ecker.
equals Ecker, right? Okay? Now, let's talk about how the electric field is going to impact both sides of that polarized molecule. So the electric field is going in this direction. What's that going to do to the negative end of that molecule? Pull it down or push it up?
Pull it down.
Why?
The test charge is
Opposite way.
It goes the opposite way, right? Because the positive test charge, this end would feel what? It's going to feel, this is going to be important. So the positive end is going to feel pushed up. The negative end is going to feel pulled down. Okay? Now, assuming that this thing, and that's the assumption that you have to make, that it rotates about the midpoint. If this is L, what are you going to use for that radius in that equation?
L/2.
So I've got torque equals Ek L/2, right? But, so this L/2 is going to be this distance. So that's going to feel pushed up, right? This is going to feel pulled down. So both of these are going to contribute to that torque. So what do you think I need to do to that equation that you have? If this is for one side, is the other side going to feel the same amount of torque? Yes, and they're both going to be going in the same direction. So could I not then double that and multiply that by 2?
Yes.
So the 2 is going to cancel out, so you get torque equals Equal. So if you're going to create a torque on a polar, and it has to be a polarized molecule, because if there is no charge on that, nothing's going to happen, because it won't interact with the magnetic field. So if you have a non-polarized molecule, this won't happen. But what you can do is, you can use that, if you have an external magnetic field, what will happen is that it will force those molecules to all line up in a particular direction. So if they're crossways, it's going to create that torque, then, because once it gets spun, once that positive end goes up there, and once that negative end comes down here, if it's already lined up, what's going to happen?
It's gonna stay still.
Yeah, it's just going to go, oh, okay, well, this is how we want to go anyway, because the negative end is going to pull that way. Now, what can happen is that you can create thermal energy this way. So what can happen is if that's a strong enough field, it can begin to basically get stretched. Because if that has some flexibility to it, and it's lined up, and that negative end wants to get pulled this way, and that positive end wants to get pushed that way, then what you can do is basically make it act like a slinky, where that thing would begin to vibrate back and forth. Well, as it vibrates back and forth, that's going to generate thermal energy, and you can heat it, and it'll generate a certain amount of heat. So here's the point. This only works if you have a positive and negatively charged particle, and the charges have to be the same, or otherwise this equation doesn't work, because then you'd have to have the two different torques, and you'd have to treat them separately. I'm not going to do that to you, okay? The charge is just going to be the same. Okay. Now, next thing we need to talk about. Parallel plate capacitors. So on this purple equation sheet where it says electricity, you all have this that says, where's it at? I gotta find it. It's weird how they do it. Let me see.
With the details.
Okay. Now, so what this gives you is the value of an electric field inside a parallel plate capacitor. So here's the short version of how a parallel plate capacitor works, and I'll show you one in just a second. A parallel plate capacitor works by separating charges within a plate, but that takes work. So typically what you have is that you have a positively charged plate, and then you have a negatively charged plate. So when you look at how this is going to play out, first off, you have to figure out what's the direction of the electric field within the plate. So if I put a positive test charge right in the middle, what's going to be the direction of the electric field? To your right or to your left?
To the right.
Or is it just going to stay in the middle?
Right.
It goes to.
Why to the right? Sydney?
It's a positive charge, so it's gonna repeal a repulsion by the positive plate and an attraction by the negative plate.
Beautiful. So this thing has two things going for it to try and push it this way. It's being pulled towards the negative and it's being pushed away from the positive. So this thing really wants to go to this way. Now, if you're going to generate electricity, generating electricity in a plate capacitor is somewhat analogous to me taking this weight and lifting it up. So if I lift it up, do I do work?
Yep.
Yes. Do I store energy?
Yep.
Yes.
So when I let go of it, it goes back to its lowest energy state. So the same thing happens in parallel plate capacitors. If you want to charge a parallel plate capacitor, that requires work. So what this is a handheld crank generator. And this is a capacitor built into it. And this is an LED light, okay? So right now, I'm going to crank this up, okay? Now, so when I do this, am I doing work?
Yes.
Why? I'm exerting the force over a distance. So what I'm going to do right quick is I'm going to disconnect that bulb. We'll get back to it, okay? So I'm going to turn this crank like this. So you'll also notice that that light bulb comes on because I was doing work. I was creating an electric field, and that electric field was going through the bulb. The bulb had a filament in there that had a certain amount of resistance. I generated so much electricity that the electrons in there became so excited, like, oh my God, this is so cool, right? And so then they started jumping energy levels, which they didn't like being up there. They returned back to their normal state, and they kick out these photons, and you go, oh, let there be light, okay? But again, I had to do work to do that. I'm not going to yell at it and go, come on, generate that, come on, okay? It's not going to happen. So I've got to force those electrons through that filament, and I've got to do work. So I'm going to crank this up. Got the light going on right now. If I just let go of it, notice that that handle continues to spin. Because what I've done, what I just did doing all that work is like lifting up this weight. Mother Nature doesn't like that, okay? So Mother Nature wants to return to that ground state. So when I was cranking on that handle, I was doing work. I was storing electrical potential energy within that capacitor. Then as soon as I stop, Mother Nature goes, oh, this is bad, not liking it. Mother Nature goes, I want to discharge that capacitor, and so it took that energy that I stored, and it made that crank then continue to spin. So now I'm going to do that same thing, okay? But then, Hold on. I gotta do this all at once. Hold that. Then I'm going to disconnect it. So what I've done now is almost like a dam. I have stored potential energy in that capacitor, okay? So I've separated this and I've created an electric field. Now what I'm gonna do is I'm gonna hook that up to this LED light. And it should have, hold on. It worked before. Hold
Don't you
on.
hate it when that happens?
Oh, there it goes. Okay. So, what I've done is that I stored all that energy. So, what's happening is that now I'm giving that energy a place to go. And now it's flowing through that circuit and it's lighting up this LED light. So, this is the beauty of capacitors. We'll talk about capacitors a lot once we get into circuits, okay? So this is just an opening salvo, is that you understand, oh, this is what capacitors do. So capacitors kind of act like batteries because of the fact that they store energy. But with capacitors, you can actually do a lot more with them because you can determine the rate at which the capacitor discharges. You can determine, oh, how much do you store behind it. So capacitors work really well, especially like if you look at your phones. So if it's dark and you want to take a picture with your phone, what do you use? A flash, right? So that flash works off of a capacitor. So your phone senses, oh, it's dark. We need a flash of light. So within your phone, there's a capacitor like that has gotten charged up. Then your phone senses, wow, it's dark. We need a burst of energy and a flash of light. So it discharges that capacitor, that electricity flows through the flashlight, the little flash on your phone, you get a flash of light, cool selfie, and it works because of a capacitor. Now, in the old way, and this is old way, and for those of you, here's a tie-in with chemistry. So, the old way that they used to do flash was based upon a capacitor, but it was a cube. It was a glass cube about ½ inch by about ½ inch. And within it, there was a strip of magnesium. If you've ever seen magnesium burns exceptionally bright. So how they used to do flash bulbs is that they would have it hooked up to a capacitor, and then there would be a strip of magnesium inside that bulb. So when you wanted to flash, that capacitor would discharge. It would basically light the magnesium on fire because it has enough resistance that magnesium would burn very quickly and produce that flash of light. And so it literally, it's like how the flashlight worked. It used to literally work by burning magnesium. Then they said, okay, hey, that's a little bit dangerous. Let's actually go to bulbs. But then you had to have a next generation of bulbs to pull that off. So here's what you got going. Here's what I want you to remember about capacitors. It creates an electric field. So the equations for a capacitor, this is the electric field within a capacitor. So Q is how much charge that there is. So what I just did by cranking that is that you would have to be told, oh, this thing is charged to 5 nanocoulombs, whatever that value is. So clearly, if the charge gets bigger, the electric field within that capacitor is going to get bigger. Now, this is what we call a parallel plate capacitor, and you're looking at that going, that looks pretty round, okay? And it is. But how they build these capacitors is that they basically start with 2 parallel plates, almost like a jelly roll. And then what they do is that they layer that and wrap it around like a jelly roll. So, because it physically it sucks trying to build, oh, I need a big capacitor. I'll just have a big plate. Well, that's cool, but it really doesn't work so well because of the fact that, oh, you don't want your capacitor bigger than the phone that you're going to put it in. It's like, the phone is small, but the capacitor is huge. It's like, oh, I'll just carry my capacitor separately. No, that doesn't work either. So what they did is that they take these and they just curl it up and wrap it like a jelly roll. Therefore, you can get a large volume within that circle. Capacitors are rated in farads, or which we'll get into later. For now, don't worry about it. Here's what I want you to get out of this. Now, this is the Greek letter tau, and it depends upon what the capacitor is. I don't even know why they bothered to put this thing on here, because it's always equal to 1. So, on your equation sheet, there is this Greek letter tau. Don't worry about it, okay? Seriously, I don't even know why they put it on there. Nobody ever uses it unless you're like a hardcore, weird electrical engineer. So just act like that K isn't even there. A is going to be your area, okay? So now let's think about this. And this is somewhat counterintuitive, but as the area gets bigger, what happens to the value of the electric field?
Decreases.
It actually becomes smaller. Now here's the justification for that. It's like you take the same amount of charge, if Q is constant, and if you spread that out over a bigger area, that charge becomes more spread out and becomes thinner. And so therefore, the strength of the electric field becomes less because of the fact that you're spreading that area over a larger space. Now, this epsilon naught. So this, if you look at this epsilon naught, and if you come over here, epsilon naught is what's known as the vacuum permittivity constant. You have two things. You have the vacuum permeability constant, and you have the vacuum permittivity constant. They're both used in Maxwell's equations for electromagnetic fields, which we'll get into later. For now, just accept that it's a number. So the vacuum permittivity constant is 8.85 times 10 to the negative 12, and it has these weird units of Newton, of Coulomb squared, then Newton meter squared. The reason that it has those weird units is because that's the only way you can get the electric field to work out to be newtons per Coulomb. So, all I want you to have out of this is just a basic understanding that says, okay, hey, this is how a capacitor works. Because obviously, if you don't charge it and there's no value of Q, what's going to be the value of the electric field? 0, okay? So, that kind of makes sense. Like, oh, okay, I got to charge it. Well, and to charge it, you can hook it up, like, for example, at night when you plug in your phone, one of the things that that does by plugging in your phone is that if you've used and deleted, drained out that capacitor, it's going to recharge that capacitor overnight. So that's one of the things that plugging your phone in at night does. Okay, so this is kind of where we kind of got to go old school. Okay? So I'm going to take, where's... Oh, come here, I don't want to go get a blanket.
Are you looking for this bag?
Huh?
Was this for physics stuff? Because it was just on my desk.
Yeah.
The only thing he's good for.
Can you stand up, Luke? Okay, walk away. Okay, well done. Okay, so Cohen sacrificed a wonderful hair job. So, here's, ooh, that's really short. Holy cow. Okay, so, when I put my hand here, and let's say that balloon goes, wow, and actually stays like right there. Actually, Cohen, I need to, where's that other balloon? Where's that balloon? Okay, we're gonna do that.
Okay, you did already. Okay, we're doing
Okay, we're just gonna make it stay right there. Now, the good thing is we're not gonna have to worry about buoyant force today.
Wait, what?
Okay, so
Again, it could only.
what are the forces acting on
This, right?
that balloon?
Tension.
Tension. Okay, tension is one.
Gravity.
Gravity, there's two.
Buoyant.
Whatever that's.
Voice in the air.
Oh, an electric force. How do you know there's an electric force?
Because magic
Being
gravity.
repelled. Now, let's think this through. Assuming that the balloon is negatively charged, what's the direction of the electric field if you were to say, hey, don't forget, just pretend that this doesn't exist. If that's negatively charged, and I want that balloon to go out, let's kind of go. Go. Come on, work with me. Go.
It's weird.
What would
gravity.
be the direction of the electric field? If this is negatively charged, and I want that balloon to go out like that, what's the direction of the electric field? To the left or to the right?
To the right.
To the right? Why?
If a positive charge goes to the right, negative charge goes to the left.
Right. So, what seems counterintuitive, because now, if the balloon was positively charged, I would want the electric field to be going to the left. But if that's negatively charged, and this is where it's counterintuitive, so I want the field to go this way to make the balloon go that way. Or that way. Okay, got it? Now, so this is why I say we gotta go old school math. Old school. Yes, we're back into vectors, okay?
Thank God.
Hey, this was yesterday's.
Vectors are so much better than some of the other stuff.
Now, like I said, you won't have to worry about the buoyant force today.
Tomorrow?
Tomorrow you will. Mainly because of the lab. Oh, you think you're annoyed with me now? You wait until I give you the lab tomorrow. Then you're gonna be really annoyed. I'm used to it though. I got broad shoulders, but it's a cool lab. Okay, so here's what you've got. So let's just say that you have. Hold on. Let me get a visual. So let's say that you have a charged particle in an electric field that's out here like this. Okay? So let's say this is the balloon, here's the string, and this thing is charged, and you're in an electric field, and this thing is out here like this. So, what are the forces acting on that charged particle? What's one of them? Gravity. Old school, right? That's just going to be Fg. Charles? Okay? So I got that. That's one of them. There's only one other force right now. If this is out here, what else do you got? You got tension. Okay?
That's energy.
You got tension.
Charles, you're cooking.
Now,
Vectors are so much.
this doesn't want to be there, right? Now, if you hearken back to the days of centripetal motion,
No.
Let's go.
okay?
Remember when this thing was my head?
There was a problem like this at the Testament, volleyball problem, okay?
Oh my.
So, as this goes around, we're not gonna do centripetal motion, I just want you to have the vision, okay? So, here's the story.
Until tomorrow.
Speaking of centripetal motion, what's the direction of any centripetal force? Towards the center, right? Okay?
Upward, obviously.
Because it's not being pushed to the outside. So, if I look at this in terms of being in an electric field, what I can do is I can resolve that into a horizontal and vertical component, right? So, if I know the weight of the object, let's make the math easy, let's say that's 0.010 kilograms. So what would be the weight of that value? What would I do? Simple thing, multiply by, and what would you get?
.098.
0.098 newtons. So then, I know the value of my gravitational force. True? Got that? So, is this vertical component here, what's the relationship between the weight and the vertical component of that string? They're the same. So if I know what this is, guess what? I know what that value is. Okay? Because that vertical component has to be balancing out the weight. True? Ah. Charles, is the wheels coming back? Starting to turn a little bit?
Yeah.
Now, let's say that the angle between the string and the vertical is, I don't know, 20 degrees. So if I know that's 20 degrees, and I know that that vertical component is 0.098 newtons, what could I find out?
The other two sides.
Oh, I could find out the other two sides. Okay? So what would the hypotenuse represent?
Those sides.
Rhymes with, remember, if you find it, what would it physically represent? Yeah, that would represent the tension that's in the string, right? Now, if this is 0.098, think this through. Is the tension going to be bigger or smaller than 0.098 newtons? Bigger, right? So if this is 20 degrees, and it just depends upon how you want to set up the geometry. If this is 20 degrees, Addie, what does this angle down here have to be?
No,
I don't know.
I don't know. I
Okay.
don't know what a triangle is, bro.
What do the sum of the angles have to equal?
Oh, 180.
So if that's 20 and this is 90, the other one has to be, it's not that difficult. No, it's really
I
not.
don't know what a triangle is.
And we're about to give you a high school diploma? I mean, seriously. I think you know what a triangle is. If I gave you a box of shapes, I think you could pick out the triangle.
Oh, not the ankles, apparently.
No, it's not the point of the story. Okay?
At soccer, we had explained the west and east
I
coast.
see a square.
Okay.
Sears.
So, here's my question. If this is 20 degrees, how can I find the tension? What would I do?
Cosine.
So the cosine of
20.
is going to equal, so
Yeah.
cosine is what over what?
Adjacent.
So do you know the adjacent?
Yeah.
The hypotenuse is your tension. So how are you going to get tension by itself? Addie, this is geometry. How are you going to get tension by itself?
You
And then divide by?
the cosine.
There you go. Algebra to the rest.
Okay.
Now, what's that vertical side that they're going to represent? The x? That's a good guess, Sean. It's a charged particle.
The electric
What are you talking about?
What would that have to represent? The force from what?
The electric field.
Ah, the force from the electric field.
Oh.
Ooh. So this side up there, which is I'm sure some of you want to say at this point, is that we could just feck it to find the horizontal component, right? So if you can find the horizontal component, then you would know the force. So then if you knew the charge on it, what could you find? Oh, the value of the electric field.
Yeah, but it's because it's charged to it. No.
Okay? Now, this
That
isn't,
visual screwed me up.
huh?
That visual screwed me up.
Oh, sorry. Okay?
So confused.
But here's the deal. So if you're going around like this, what does the horizontal component represent if you're going around in a circle? Your centripetal force. But if you're a charged particle in an electric field, the horizontal component is going to represent the electric field. Okay, keep that in mind. All right. Now, this will make sense. This is just a quick refresher. That the volume of a sphere is 4/3 pi r cubed. Okay? You're gonna need this number, okay? You're gonna need this equation. Because one of the things that you're gonna find is volumes of beads on this assignment. So, I have stuff to hang out.
Yes, bees. What's the dumbest thing you had to explain somewhere?
Good question.
No, this is not all of your assignment, this is just one part. No, it's not, but it's.
It's the bees.
No, this part
Thing you
is
had
bad.
to explain to someone.
It's not
I
bad.
don't even know.
Stupid field.
I have to explain to someone.
Oh, that's nothing.
Gambling.
We've done
No,
this.
it was just like, oh,
We did this once. We literally did this once.
they charge. If you think about it, it's not just gambling.
Hey, gambling.
It's gambling with your kids. I like those odds.
This is, we've done these literally yesterday. I'm kind of sad you took away my drawing.
I assume that second part of that.
Really?
Yes.
Well, I mean, you draw
I
on
haven't even looked at it yet.
Yes, you do. Anytime you explain a.
Because it's convenient.
You said.
It was all finished.
Honestly,
He was really kind about it.
Yeah.
if I'm being honest, I think that's the decision, but I just can't. Please, no more. Don't add another. No.
What is going on?
Burkamp, you can stop.
No.
I'm done.
So much.
He added a dash.
Hey,
Now,
Dashes are.
gaps on. What does the dash mean between the 63 and 68?
In between 63.
Yes, not just 63 and 68.
no, there was like three.
If I wanted you to do 63 and 68, what would I put?
Hey,
Okay,
We just put a comma there and call it.
when you get to question number 38, 38, you gotta go old school chemistry, okay? Like molar mass, Avogadro's number. I'm just telling you. So, on 38, let me save you a little bit of hassle. 1 mole of copper has a molar mass of
Exactly. Just
and Avogadro's number is 6.02 times 10 to the 23rd.
Last year,
And give you some questions not the electric field at the origin.
I'm not gonna do that much for this one.
was it
Now, on that multiple choice sheet that I gave you,
either? I just don't like it.
okay, listen to me. On this first one, these are like, and you can just answer them up here if you want. But with this one, don't just tell me a value. Define it in terms of either like to the positive x, to the negative x, positive y, negative y. Okay? So on these, because an electric field is a vector quantity, you need to specify which direction that is going. Positive x, positive y, negative y. Ultimately, this is a multiple choice question, but I'm just trying to guide you through it. When you get to that second question on the multiple choice, visualize this. You have a metal conducting sphere. Within this sphere, you have put one single electron, okay? Conducting sphere. In this, you put one single electron. The rest is a vacuum. You put one single electron on the inside of it. You want to figure out what's the direction of the electric field on the outside of it. Let me give you a hint. Think through what's going to happen with that electron in terms of the chihuahuas inside that conducting sphere. Which direction are the chihuahuas going to move because of that electron? Are they going to move to the outside? Are they going to move to the inside? And then how that is going to determine what's going to happen with the electric field on the outside of that. And yes, there is one multiple choice question on the back side of this. This one, you don't have to do the steps like the first one, but it might be something that you think through. I'm done. Good luck. You're on your own. Let me give you a hint on 38 before I forget. Your answer to 38, when you get done, which is a whole bunch of calculations, your overall answer should be 10 to the negative 11th.
On which one?
38.
38?
That's going to be your order of magnitude on 38 is 10 to the negative 11th.
Oh, yeah.
I haven't drawn it. You don't have to draw it.